Welcome to my presentation on entropy, enthalpy, and Gibbs free energy. Thermochemistry is a branch of chemistry that focuses on heat energies associated with chemical reactions. So heat is transferred between a system and its surroundings as a result of a temperature difference because energy passes from a warmer body to a colder body. Through collisions, molecules of the warmer body lose energy, and heat is therefore transferred into the temperature until the temperatures become equal. So in an exothermic reaction, there's a temperature increase, and therefore the heat of reaction is negative. In an endothermic reaction, there is a decrease in temperature, which means the heat of reaction is therefore positive. Each of these reactions either give off heat or gain heat from its surroundings. So enthalpy is a state function and is defined as the sum of the internal energy and the pressure volume product, where delta H equals delta U plus P delta V, and at constant pressure the heat evolved is equal to the change in enthalpy. The modern interpretation of entropy is firmly rooted in the idea that microscopic systems is made up of tiny particles, and because those particles are in continuous random motions and experience collisions with each other in the walls of the container, the positions, velocities, and energies of individual molecules change from one instant to the next, meaning there are many possible microscopic configurations, also known as microstate. A microstate is characterized by specifying the quantum state, which is the quantum numbers and energy of every particle. So entropy is a thermodynamics property that is related to the way in which the energy of a system is distributed among the available energy levels. So this guy here, Ludwig Boltzmann, associated the number of energy levels of the system with the number of ways of arranging the particles. So in this equation, delta S equals kB ln of W, where kB is the Boltzmann constant, and W is the number of microstates, and delta S is the entropy. So there are four different situations in which entropy increases. So the first one is when liquids are formed from solids. The second one is when gases can be formed from liquids and solids. The number of molecules of a gas increases in a reaction, or the temperature of a substance increases. And as a common rule to relate entropy and spontaneity, if delta S is greater than 0, then the process is spontaneous. If delta S is less than 0, the process is non-spontaneous. And then if the delta S is equal to 0, the process is reversible. So let's explore a hypothetical process that occurs at constant temperature and constant pressure. So Gibbs free energy is shown in this equation by delta G equals delta H, which is the enthalpy, minus T, which is temperature, times delta S, which is entropy. And so we can see that if delta G is less than 0 or negative, the process is spontaneous. If delta G is greater than 0, meaning positive, the process is non-spontaneous. And then if delta G equals 0, the process is reversible. Relating this to the entropy rules that we just discussed in the last slide, we can compare delta S and delta G. But remember that Gibbs free energy must be at constant temperature and constant pressure for this rule to matter. So the standard Gibbs energy of reaction is defined as the Gibbs energy per mole of a reaction, and much like how we find the standard enthalpies and standard entropies, we have first this equation where we have A plus B equals C plus D, and then the corresponding coefficients in front. And then we have delta RG equals the products minus the reactants, and then we're going to get the values of the Gibbs free energy from a table in the textbook. And then obviously on the side we see a rule here. This is very important to note down. So in one case, if delta H is negative and delta S is positive, delta G is therefore negative and it is therefore spontaneous at all temps. On the other side, if delta H is positive and delta S is negative, then delta G is going to stay positive and therefore the reaction is non-spontaneous. But what happens if delta H and delta S are either both positive or both negative? That's going to change what delta G is. And so depending on what delta G is, whether it's negative or positive, it can be spontaneous at low temps, non-spontaneous at high temps, and so on. So it's important to note that down when looking at this slide. So the equation we just saw was for Gibbs energy in standard conditions, but what happens when Gibbs energy is in non-standard conditions? We would then use a different equation, which is shown below as delta Rg equals delta Rg of the standard conditions plus RT ln of Q, where Q is the reaction quotient. Q can be defined as the partial pressure products over the standard condition divided by the partial pressure reactants over standard conditions for gases. For liquids and solids, the activity is always 1, and for solids in an aqueous solution, the ideal solution behavior assumed for the activity is replaced by molarity. Bioenergetics is another example of a real-world application because the oxidation of glucose to carbon dioxide in water is accompanied by a large negative free energy change. The breakdown of glucose is a series of steps in which the energy is liberated at each stage and will be captured by energy carrier molecule, also known as ADP. At each step, ADP molecules react with inorganic phosphate and changes to ATP. Free energy is released when the molecule travels to a site where it is needed and loses one of its phosphate groups.
For our first question, at 298 Kelvin for the given reaction with a standard molar enthalpy of negative 620.2 kilojoules per mole and the standard molar entropies as shown, determine the Gibbs free energy at 298 K and whether the reaction proceeds spontaneously in the forward or the reverse direction when the reactants and products are in their standard states. So first, when we're looking at this equation, we notice that PCl3 and POCl3 has a 2 in front of each. So when we're putting that into our equation of standard molar entropies, we want to make sure we put a 2 in front of each. So when we're inputting our values from the given molar entropies from the equation, also which you can find in the Appendix D of the textbook, we can input our values and get 222.4 minus 2 times 311.7 minus 205.1. And then if we put that in a calculator, we would get negative 383.7 joules per Kelvin mole. And then using this value that we found, and then the molar enthalpy given in the equation, we can use that to find the Gibbs free energy. So inputting our values, we get negative 620.2. We want to make sure this is in joules, so it's times 10 to the 3 joules per mole minus the 298 Kelvin. Minus the value we just found, 0.7 joules per mole. And then putting that into our calculator, we would get negative 506 times 10 to the power 3, but we'll just change that to negative 506 kilojoules rather than joules per mole. And so if we want to know whether the reaction proceeds spontaneously in the forward or reverse direction, it will proceed spontaneously in the forward direction because delta Rg is less than 0. For our second question, a possible reaction for converting methanol to ethanol is this given reaction. Use the data from Appendix D to calculate the enthalpy, entropy, and Gibbs free energy for this reaction at 25 degrees Celsius. Again, remember to look at the values from Appendix D so that you can input them into the equation. For time's sake, I've already finished the equations for you, but I do encourage you to do them. They're the exact same steps as the other example we just did. So we're going to be focusing on B and C. Is this reaction thermodynamically, dynamically favored at higher low temps or at higher low pressures? And then estimate K for the reaction at 758 K. So first for B, we're going to look at the delta RH. Delta RH is a negative, so it's less than 0. That we know. So because it's less than 0, it is thus favored at low temps. And then if we look at the number of moles of gas for this given equation, we see that on one side there's positive 2, but then on the other, take away negative 4, we get how many moles of gas? We get negative 2. And because negative 2 is less than 0, we therefore say that the reaction is favored at high pressures. And now for this equation, it's very similar to what we would have done here, except a different temperature, 750 K as said in this example. So inputting all the data that we found in A, and then as well as including 750 K for the temperature, we get the value of positive 4.9 kilojoules per mole. And then we make this equation equal to negative RT ln of K, which is just a different equation for Gibbs free energy. So making them equal to each other, we can then find what K is by dividing out negative RT. So ln of K equals 4.9 10 to the power of 3 joules per mole over negative RT, which is this is that constant, so it's 8.3145, and then this is the temperature, which is 750 K. Inputting this into our calculator, we get ln of K equals negative 0.79. And now to solve for K, we would do E equals to the power of negative 0.79. Putting that into a calculator, we would get K equals 0.5. So that's how you would solve that problem.
Thank you all for watching.